Hello and welcome back, everyone. We are trying to write a toy kernel for an operating system from scratch. Last time we've, put the last touches, the finishing touches on the first stage of the bootloader to make it configurable. And today we are going to start work on the second stage of the bootloader. Of course, the first item we'll address is the physical memory mapping. So let's get to it. So here I've created a new folder. Actually, I did a bit of housekeeping to move the first stage of the bootloader that was in this bootloader folder to a stage 1 folder. And also I've changed the makefile accordingly to point to the correct build directory. And I added a makefile in the bootloader folder that actually calls the stage 1 makefile, right? So let's get started for the stage 2. Create a new file. I'll call this one start.asm and let's get started. So if you remember from what we did last time, we have loaded ourselves, basically we have loaded the second stage to 0x800, right? So let's give it that address to tell the assembler that we are getting loaded there. So using the org directive, right? And then we are still using real mode, so U16. Right. And here I want to, do a quick recap on how we are using memory. So do a quick memory map for our current situation, right? So memory, silicon type, memory map. So here we have 0500 to, actually, let me just add another 0 there, to 0600. That's for our stage 1 stack, right? If you remember correctly, the stack starts at 600 and it grows up to 500. Then we have so 0x. Actually, just to be very precise, this would be 5ff, right? Because it doesn't reach 600. Right. So 0x 600 to what was it? 0x 7ff, so just shy of 800. Actually, let me just align that correctly. This was the stage 1 code. This is where we relocation, right? Where we relocated ourselves from 7C00, right? And then what we have is that at 0800 to some address that we don't really know, because this is the stage 2 code as loaded by stage 1. And this, so we have a small issue here, is that we don't know where our stage 2 ends. So we don't really know where we can put where we can load our kernel, right? So what we are going to do is we are going to assume that it's going to be quite large, and we are going to give it wide berth, and we are going to assume that this would go all the way to let's just put this in here for now, okay? So this makes it so that if we need any code later, we can just put it in here. And I guess this would be our, buffers. Yeah, just maybe buffers if we need some buffers. And also another thing is that now we don't really need this code anymore. So what we can do if we ever need a stack for stage 2 is we can just say that this whole thing here would go and be the stage 2 stack, right? So it would go from 7ff to 500, right? So this would be stage 2 stack. Right, so now that we have our memory mapped, let's get started on doing actual memory mapping. So what we need to do to memory map is we can use the good old BIOS infrastructure to do that for us. And so let me just go back to the browser quickly. Right. So here you can see that on the BIOS interrupts, if we look at interrupt 15, and we go here down to E8, you can see that we have this one here, E820, 15E820, which is newer BIOSes get system memory map. And if we go into there, you can see that it takes some parameters and then it returns some result that's in here. Yeah, it's not there, it's here. So basically it will return us a range. So the base address for this memory range, the length of it in bytes, and then the type of the address range. And the type can be one of these values. So 01 is memory available. So it's a free memory, basically. We can use it however we want. 02 is reserved, usually either by system RAM or some memory map device. So this is memory we have to mark as used so that we don't allocate it to some process and have it overwrite it for some reason, because that can cause some very bad things to happen. 03 is ACPI, and we'll discuss what ACPI is later on, but for now, ACPI, let's just say, is some specification that will let us communicate with the motherboard and other peripherals and see what the system is actually capable of. So ACPI reclaim memory, this means that this memory can be used when we first query the ACPI tables. But once we are done with the tables and we have all the info we need, we can just reclaim this memory and mark it as free and use it. And 04 is the NVS memory for ACPI. This is required to be saved between sessions. And that means that basically we treat this as unusable or reserved memory, right? And any other ID value here, other than these four, would have to be treated as reserved, right? So this is what we are going to do. So let's look at the recipe here for this call. AX should contain E820, EAX. Yeah, we don't really care. So the important here is just EAX needs to be, so the higher word of AX needs to be zeros, right? Then EDX needs to have this word in it. Yeah, so this is SMAP, system map. EBX contains the continuation value or zero to start at the beginning of the map. Okay, so I guess EBX would have some sort of stopping condition for us. ECX would be the size of the buffer in result, should be larger than 20 bytes, but actually if we go back here, we have a keyword which is 8 bytes, another keyword, so 16, and here we have a D word which is 4, so we actually just need 20 bytes. So we'll just ensure that the buffer is exactly 20 bytes wide. And then ESDI would be the buffer for the result. So basically in DI, we will write the address where we want to have the result. Right. Also, so the return is CF is clear if successful, and we have EAX. Basically, we have the value we had in EDX copied to AAX to indicate that we successfully did the read, then the buffer we give it in DI should be filled, and EBX would contain the next offset from which to copy, or 0. So if we have 0 in EBX, that means we are done. And ECX would contain the actual length of the bytes read. But in our case, it should be always 20. So we don't really care about this. I guess this would only be an issue if you have a broken implementation of BIOS, but we will not care about it for now, okay? Right, so before we write the code to map the memory, we need actually to ensure that we have our magic bytes in place, right? Because we expect the first 2 bytes of the second stage to be F4H and I guess 1CH, if I remember correctly. So let me just check that, F4H and 1CH. That looks good. And then we'll have our start label here, and it will be just after the 2 bytes, right? And of course, we'll just XOR AX and do some basic housekeeping or the setup for our segments. Let's zero out these 2 segments, DS and ES, and then we will start working on our memory map. So the way we want to do this memory map is basically, let's take a look at the recipe again. So AX needs to have, so basically we need to zero out EAX and then put 0820 in AX. And then we need to put EDX, that value in EDX, and we need to zero out EBX to have the to have it start at the beginning, because we want to read the full map. Then we have to give it a size. This would be just a constant, I guess, would just be 20. And then we will have, okay, so this is the thing that we will have to decide. We will need to decide where our buffer will need to be in memory. Okay, so let's go back to code and start working on that. Right, so let's XOR EAX, then move AX, what was it, E820H, remove D word EDX, and I'll just go ahead and copy that value, and there we go. Actually, just replace it with this, so it's a bit readable. And actually, what we can do here is, so you have to remember something. The bytes will be read in Little Indian. So this is smap. So smap, right? P is 50. But if we want this to be read from memory, we can actually do something very cool. We can just give it a the string in reverse, and it will basically set the bytes for us, right? We can do this, and we'll have the correct value since the bytes will be read in the reverse order. But let's not do that for now. Let's just keep it there. So yeah, we also have to XOR EBX, right? So we can read it from the start. So the EBX contains the 0. And then we will have to, I guess, put in DI. So move DI some buffer here, right? So this is something we need to decide. And of course, we also need to XOR ECX with itself and move to CL the value 20. There we go. And this would have to be a word, I guess. Right, so let's discuss how we are going to do this. So here we have, in our memory map, we know that the first address that we can write to, as we decided before, would be this 0xA00. So let's just set that as our buffer, right? So I'll call it mmap buffer, and also equal to a 000, and here we'll just delete that. We want this to be at mmap buffer. Right. The only issue here is, no, actually there's no issue. So we just need to call int15 h, right? And yeah, and do the checks for the result. So what we need to check is we need to compare EAX with this value here. And actually before that, we need to check that the carry flag has been set or not. So jump if not carry. No, actually, never mind. Jump if carry, because the carry is set if there is an error, right? So here we will have a label that we will call mmap. Let's just call it no mmap, right? No memory map, and here we'll go ahead and do the no memory map label. And actually we will need to print something to the screen. So what I will do is I will actually go ahead and import the functions we've written for the first stage to the panic and print functions that we've written for the first stage, right? So let's just go ahead and do that. And if I remember correctly, we also need to, we had a macro, there we go. So this macro here, right, there we go. And here we'll have to, actually, hold on, let's just do something, right? So let me just go here, create another file. I'll call it macros.inc. And I'll put my macro into there. And I will also probably, let's see, can I move these functions? So I guess we have this panic prefix that we need to define, and it still needs to be in this file. Otherwise it will move our definitions. But otherwise, I think we can just put this whole function into, I guess, another file. Let's call it helpers.inc. And if it doesn't work, we'll just revert back to what we were going to do. And here what we will do is we'll go ahead and include, so I guess helpers.inc. Yeah, it's helpers with S. Include macros.inc. Of course, inc. Let's go. Right, and that should be fine, right? So here we just need to define variables and have that panic prefix that we need. So let's just define that, and we will call it, just call it fatal, right? That will be our prefix. And here, so what we will do is the usual, so move si mmap error, and then jump into, what was it? Panic func, I think it's called. Okay, no, it's panic func, right? And here we will need also to define the mmap error, and that would be a byte array that says couldn't map memory or physical memory. Couldn't map physical memory, and here with the 0 afterwards, right? So that's fine. Right, and here we have the memory buffer. Actually, let me just move the memory buffer after the after this, and have this at the very top of the file, just so that it's clear what we're trying to achieve. Right. So now that we have this, if we have no carry, that means we failed, we jump to the error. Otherwise, we check the EAX, because we, let me just go back to the recipe. Yeah, so EAX, we expect it to have the smap bytes, and let's do that. And if it doesn't, so jump if not equal to same thing. So mmap, no mmap, nah, mmap, no mmap. Right. So we might also check that EBX is 0. So I guess test. Yeah, let's just test EBX itself, and if it's 0, we want to right, so if it's 0, we'd want to go to mmap done, right? Have that somewhere here, or just call it mmap and for now, and have that here, mmap and that would just be nothing, right? And we'll also add the forever loop, just so that when we run this, we don't get weird stuff. Because if you don't have this forever loop, the CPU will just try to execute whatever instructions it finds. So on the VM, it will find a bunch of zeros, but on actual hardware, it can actually find some weird bytes, and it will try to execute them as instructions, which might lead to some weird behavior. So let's just jump to forever. Great. Right. So what else do we need to do? Okay, actually, let me just replace this, because we don't want to have an AND for ABX. We just want to see if it's 0 or not. And if it's not 0, well, if it's 0, then we have basically finished the mapping, right? Okay, so here we are reading the first map, and if we want to read the next ones, we will have to basically loop this around until EBX goes to 0, and then we will jump to mmap and, right? So actually, what we want to do is we want to have this memory map, and we want to pass it to our kernel, right? So we will need to define some sort of structure that the kernel will be able to read, so that it knows that we've mapped the memory and we give it the actual memory map, right? So let's try to define that structure first. Let's try to define that structure, and we'll just go ahead, I guess, and create a new file. I'll call it structs.inc. Yeah, let's call it structs for now, and we'll see where we go from there. So here we have. So okay, let's define the struct, and I'll try to call that struct booinfo, just so that it's clear what it does. So booinfo, and it will be virtual at bootinfo, right? And virtual. Right, so what will we need to pass to the kernel? I guess the first thing we need is a size, so that it knows where to stop reading our boot info. I guess that would be a single byte would suffice for that. Let me think. Yeah, I think a single byte would suffice for that. Right. No, actually, a single byte will not suffice for that, because what we will assume, we don't know how many memory maps we have. Okay, so we can really have large memory maps, especially if we have a lot of devices that do memory map I/O. So the memory will be segmented to a bunch of smaller chunks, right? So we can have a lot of memory areas that we can use. So we don't really know how many memory maps we have. So this size here, I'll just put it as a double for now, and we'll see how it goes. And then I guess we will need a, let's call this bootloader. And this would be just a single byte, I guess. And this would basically, so this virtual info is our contract with the kernel, right? So whether we load the kernel using the BIOS bootloader or any other bootloader, being BIOS or UEFI, we'd still pass the same boot info structure to the kernel, right? So here the bootloader, what I want to put here is the type of the bootloader that was used, so that the kernel knows, even though it might not care, but let's just give it that info for now. So here we call it bootloader BIOS, and we'll set it to 0, and bootloader UEFI, and set it to let's say to 1, I guess. Okay. Right, so what else do we need? Bootloader, I guess we will need to pass it the So I guess we need to pass it frame buffer information, right? So frame buffer information for the video stuff that we'll do next time. So let me just try to fill those in. So we'll need the pointer to the start of the frame buffer, and that would be a quad. And then we will need, I guess, the width of it. This would be just a double, I think, would be fine. And then we'll have the height of the frame buffer. And then we also need the stride, or bytes per line, or scan line, however you want to call it. I'll call it scan line, so it's clear. And we'll discuss all these in detail when we do the video stuff next time, I think. Right, so now that we have this, we also might want to, oh yeah, of course. So we also need to give it the frame buffer, I guess, pixel format. So pixel format. I don't know if there is a better way to name this, but basically it's the order of pixels for every color. So you can have pixels being arranged in the classic ARGB, or you can have them swapped around for, so basically you can have BGRA or any other, I guess, rotation of this combination. So this would need to be, I guess we'll use a sort of enumeration for them. So let's just set them as a byte for now. Right. And you know what I will do is I will also add booinfo.magic, just so that if we ever need this to be found in memory, we've lost the address and we need to scan memory to find it, we can do that, right? So I'll just use a double, which will give us a 4-byte magic value that we can look for. Right, so what do we have here? We have 4 and 4, that's 8, and 1 and 1, that's 10, and then we have 12 here, so that's 22, and then we have 8, so that's 30, if I'm doing this correctly. Right, so these here is what I like to call the platform independent stuff, right? And I want them to be, so what do we have? We have 30. So let's say that this would be 64 bytes. Okay, so just so that if we need to add other stuff or make some of these bigger, we can. And so what I will do is I will actually pad this to 64. So now we have 30, so we need 34 bytes of I guess just padding, right? So bootinfo dot unused, just call it unused, and then 34. That's I guess we will probably need to split that into so 4 quads, right? 4. Let me just do this way. So this would give us 32, right? And then we will have bootinfo unused 2, and here we need 2 bytes, right? So db00. Okay, so this whole thing now is 64 bytes, and now we will have the I guess platform dependent stuff here. Right, so how big do we need this platform dependent stuff to be? I guess we can just go for 32 bytes for now, right? And this platform dependent stuff we will, so let's just set up this for now. Since we have, if I go back to the browser, you can see that we have a ACPI memory region. So what we are going to do is, since we will need to scan the ACPI memory region, we will try to avoid scanning the full memory if we can. So we just want to get the first pointer we get to the ACPI memory and give it to the kernel as a way to tell it that it needs to start scanning from that address and not from the start of memory, right? So let's go back and do that. Right, so I'll just give it ACPI pointer. This would be a quad, I guess. And let me just pad the rest. Bootinfo unused. So that's, let me just give it a 0-based index so that I know where we are. So 0, 1, 2, and this would be quad, and we have 3 quads here. So this makes 4 quads, which is 32 bytes, right? Okay, and here we will have our memory map. And the way we are going to lay out memory map, since we don't know how long it is we are going to say that it basically goes from this address here that I'll call booinfo.mmap, and I'll actually set it up as a label so that we can get the address of it using the colon. And we'll basically say that it goes from this address here all the way down, and we will know where to stop with this size here. So we know that this this part here is 64 bytes, and this part here is 32 bytes. So we know that the total is 96 bytes. So anything above 96 on the size is basically the size of the memory map. So we can know in advance how big our memory map is and what to expect. And one other thing I want to change is that here we have, let me just make this a bit bigger. Here we have the base address as a keyword, right? We have the length as a keyword, but we have the type, which is one of these values, as a double word. But if you look at these values, you can see that we are wasting quite a bit of space using a double word for it. What is more is that all the base addresses and the lengths, we want to have them page aligned. And a page in, well, it depends on the architecture, but a page on x86, the smallest page is basically 4K, so 4096 bytes wide. And 4K, if you remember correctly, is 1000. So let me just pull up the calculator. There we go. So if I pull up the calculator and just type in 496, you can see that it's hex 1000, but you can also see that in the binary representation, we have the full lower byte as zeros always. So it can be, so let's multiply this by, I guess, 11. And you can see that no matter how you shift it, the lower byte, actually the lower three half bytes, I guess, the 12 lower bits will all be zero. So this gives me an idea, which is instead of allocating a full D word here just to store the type, why not just put it in this lower byte, right? That's always zeros. And we can just do a simple AND with a chosen mask to basically get it back, right? So that will make our structure go from 20 bytes long to just 16, which is quite a bit of memory saved if we start to have a lot of, I guess, chunks to map. Right, so let's go back. Let me just go back to the code. Right, so let's go back here. So first things I want to do is just include, actually just put it here. So include, what did I call them? Structs, yeah. It helps, structs, great. It helps if I type it correctly. And actually, so what did I call? Yeah, I call it booinfo. So I'll just come here, right, and change this with booinfo. And actually, what I also want to do is I want to initialize our booinfo because init booinfo. So because we're pointing to a region of memory that we don't really know what happens there. So yeah, we are going to initialize it. So let's go ahead and do that. So what did we put in first? So the first thing is magic, right? So let's move the word to EAX, and that would be I guess booinfo magic, and we'll need to define this. Let's just define it here, right? Booinfo magic. This would be, let's choose something, yeah, let's just give it 4 bytes that are hard to find in any sequence of code, all right? So boot magic info goes into EAX, and then we will move the word, so we'll move EAX into booinfo.magic. And then what we will do is we will zero out EAX, and then we will move the word to, what's the next field, we want a size. So actually, we don't need to zero it out yet. But in size, we know that this is, so this whole thing here is 96 bytes. So let's set it as 96. And when we start finding memory map chunks, we will increment the size, right? All right, so now we will zero out that, and we will move dword to booinfo dot bootloader. Okay, so we still have stuff to do. Let's just put it here, and here we want it to be this here, right? Let me just copy that and set it there. Okay, so move dword bootloader info frame buffer pointer, which is a quad, so we'll do move twice. So frame buffer pointer, and we'll move AX to there, and then we'll do it a second time. Just duplicate this, and we'll say that we'll move four bytes, and then we'll do it a second time, which is the second half of the quad, right? And then we have the width, height, and scan line. So we just duplicate that a few times, and go ahead and do frame buffer width, frame buffer height, and frame buffer scan line. Not scan line. Right, and we will also need this frame buffer pixel format. Right, so let's just duplicate this and have it set to 0 pixel format, and this would be a byte that we are moving. Okay, so the unused, we don't really care about them because we are not planning to use them, and here we have the ACPI pointer. We'll give it the same treatment as we did for the frame buffer. Oops. Right, so let's just do this, and hit with the ACPI there. I guess we're pretty much done. Yeah, I guess we're done. So, okay, so let's get this going now. So what we needed to do is we need to loop on this query here until we find EBX being 0. So what we'll need to do now is that if EBX is not 0, instead of jumping to and, what I want to do if it's not 0, so if EBX contains something, I want to jump to a label that I'll call next map, right? And that label will start somewhere. Let's just start it somewhere here, right? So next map. Right, so now we need to do some, we need to move some things around, okay? So this XOR ABX, we don't want to do it on every map because we need ABX to conserve its value so that we know where to continue from. So this will go up there. This XOR will need to have, I think, even though we don't really need it, but no, actually we do need it because AAX gets overridden with this value. So we need to XOR it every single time, right? Or maybe we can just go ahead and I guess move, maybe we don't need to do the XOR ever. We might just want to tell it to move this to AX, and that should be enough, I think. Right, so what else do we need to do? Of course, yeah, we need to move, so we don't want to move the bootinfo, and actually this would need to be bootinfo.mmap, right? So it's the label that we've created here, bootinfo.mmap. And we don't want this to be moved to DI every single time, because if we do that, we will override the same entry every single time. So this will have to be moved out of the loop. This is the loop initialization. The ECX, I guess, gets overridden, so we'll just keep that there. And I guess that's it. Right, so this is our loop, this is our query. And what do we want to do here is once we have the map, so here right after we confirm that the map is good, we want to actually do the trick we wanted to do with the type. So we want to move the type to the I guess to the base address last byte. Okay, so here is how we are going to do that. We know that di is actually a pointer to the first to the base address. If we do this here, so di points here, right? So if we want to get the type, we just need to query di plus 10h, and the h is 16, right? So di plus 16 would give us a, as a d word, would give us the range, the address type, right, of the address range. But we don't really care about the full d word because we know that the values that we care about are just these. So we just take the full, the first byte of the d word. So let's do that. Bring back the code. So let's move into AL since we are resetting AL every single time, so we can use it as a scratch register. So let's move into AL the I guess the value that's pointed to by di plus 16. So this would be the first byte of the type, or rather the lowest byte of the type, since assuming little Indianness. And this would give us the value that we're looking for. And then we will move this this value. But what we want to do also is we want to mark it as our own type, right? So what I'll go ahead and do is I'll create a an enumeration of the memory types that we want to use, right? So this used would be I'll set to 0, and have free would be 1, and then we'll have mmap. I guess ACPI would be 3, and then mmap reclaim. This would be 4, right? This basically is our own struct that lets us define the memory type for the map. So that if we can see, if we see that it's a reclaim, we don't really care if it's ACPI reclaim or any other stuff that we are using, because we might want to use some memory as a scratchpad for this second stage. And once the second stage is done, we want to just have that memory be freed, so we can just mark it as reclaim, right? Okay, so now what we will do is we will start comparing that value in AL with the actual values that we have. So we know that 0, 1, actually let me just copy those values here so I can see them better. Right, so I just hit it with that, align that. All right, great. So here, so 0, 1, compare AL with 1, right? If equal, we'll just have to go to a label called free. Then we compare it to, I guess, 3, which would be the reclaimable, and then we go to reclaimable, mable, there we go. Then we go to compare AL with 4, which would make us jump to ACPI, right? And for anything else, we'll just move into AL. So here, if we arrive here, that means that the memory is used actually. So here we are, and I also actually forgot about this. Any other value is considered reserved, right? So here we are doing is we are checking for 1, 3, and 4, and if we have any other value, which is 2 or any actual other value, we just consider it as used, right? So here what I'll put into AL is mmap used, right? And then I will, so I need to jump to some, I guess, some label. And here we'll do a neat little trick. So in FASM, you can use @f and @b to jump to anonymous labels. So basically @f will jump to the next. F is for, I guess, following, and b is for before. I guess that's a shorthand I remember with. So f would just jump f at f will jump to the next, the first neighboring anonymous label, which is annotated with double @, right? So and if we had some other anonymous label here, and I wanted to jump to the one before, I can just do @b. It's a neat little trick we can use. Right, so here what we want to have is we want to have, so first of all, the labels that we've created. So free, the reclaimable, and ACPI, right? And every one of these labels would just do a move AL, mmap, and the type of the mmap, and then it will just jump to jump forward to that anonymous label that we've set here, right? Move AL, mmap, reclaim, and jump to that forward label, and then ACPI, of course, will do exactly the same. So move AL, mmap, ACPI, we've called it, and then it will, I guess we don't really need to jump anywhere here because it's the next instruction, so it's fine, right? So here what we need to do is we need to actually set that value to the lower byte of the base address. So let's do that. We know that the base address is still in DI, right? So let's move the byte to the value of DI, so the first byte of DI. We move AL to it. That's it. Right. So here we have this as used, and here we will just move this or here because it needs to go all the way down here. Right. So what we need to do now is, first of all, increment DI, because we need to go to the next, I guess, spot on our memory map. And since now our DI, our memory map struct, I guess, is just 16 bytes long instead of 20. So we just need to increment DI by 16, right? So add DI 16. And then what we need to also do is, right, yeah, something I've forgotten is to do this. So we need to increment the size of the bootloader by 16 also, because we've successfully read one map. So we need to register that we've read it by incrementing that size, right? So now that we have incremented this, now we're starting to have an issue, because what if something happens and this just keeps going on and on and on? We want to have some guarantee on the maximum size this virtual, or rather this structure booinfo will be. And what we are going to do is we are going to assume that the maximum size booinfo will take is a full page, right? And that brings us here, and that makes it so that this at the worst possible value, we just go from A000 to AFFF, right? So this would be bootinfo at maximum, right? And here we will go from B000 to whatever is the end of our memory for other buffers that we might need, right? But now our memory map looks like this. So what we need to do now is we need to check if we are crossing this page boundary, right? So let's go here. As soon as we increment di, we want to compare it to the, I guess, we want to compare it to the address where we have bootinfo, right? Plus 4,000, plus one page, 4K, right? And if this di goes above that, so jump if above or equal to, I guess, mmap and, no, actually, we need to do some check before we jump mmap and. So let's just call it abort. You know what? Let's reuse that trick we had before. And here we will add a another anonymous label. And what we want to do here is we found out that we've reached the end of the page, but have we actually read any memory map? So that's the question that we want to know. So if we haven't read any memory map and we reach the end of the page, that means that something went very wrong. So we want to continue on and panic, right? Otherwise, we just want to go to the end and say that it went well. So here, what we want to do is compare the value of bootinfo dot size to the minimum size that we know we can have, which is 96. So 96. And here, if we are, I guess, if we are above 96, we will jump to mmap and, otherwise we will just panic. Okay, hope that's clear enough. But this is what we are going to do. And we still have a few things we need to cover for our loop. I guess we can just get rid of this, because now we go ahead and do this compare anyway. We or ABX, if it's not 0, we go back to the next to get the next map. So we call the interrupt to load the next entry of the map. BX value is not overridden here, so it's fine. Then we compare it, check if it went well. We do the check here for the carry. If we find the carry, that means that we have no map and we panic immediately. If we compare AX with the value that we expect. If it's not equal, then we panic again. Otherwise, we move the size, the type into AL, and we compare it with the values that we know. So 1, 3, and 4, which are the values that we are interested in. If it's 1, we go to 3 because 1 is available memory, and we put in the value that we set on our enumeration in AL, then we jump forward. Same thing for AL. AL is reclaimable, so we jump to reclaimable. And 4 is ACPI memory, which is marked as ACPI when we jump to ACPI. Otherwise, we just mark the memory as used and we jump forward. So all of these basically fall through to this. And here we move whatever we decided to put in AL, the enumeration value for the memory type, into the last byte of the base address. And we increment the size, we increment DI with 16 bytes, and we check if we cross the maximum allowed size for bootinfo, which is 1 page. Actually, what I want to do is I'll just go to structs and I will do max bootinfo size, and I'll just set to 0x1000, which is the same value as actually let me just make it clear by saying as a decimal value, right? Right, so let's just replace that with that. So we compare that di didn't cross this value. If it did, we jump forward to this, sorry about that, to this label here. We compare that we have an actual memory map. We've read some of the memory map. If we did, we go to the end here, which means that everything went swimmingly. Otherwise, we panic. And if it's not above, meaning that we still have some size left, we check that bx is not 0. If it's 0, then we fall through here and we do the same thing. If we've read something, we go to the end. Otherwise, we haven't read anything and we can just panic. And we loop back to this start. Right, so it looks fine, I think. I think we did everything correctly. So now let's try to make this run. So let's make this run. And the first thing we need to do is, of course, create a makefile. So let's do that. File, makefile. And yeah, because I'm lazy, I'll just go ahead and copy this makefile I have here. Right, so this would be stage2.bin, stage2.bin, and here we'll have start that goes to stage2.bin, and then we copy it. Actually, let me just do something like this to avoid typing it. Actually, I should have done it for this one too. Yeah, it's fine. Stage2.bin, the output there looks good. Right, so we need to now edit this makefile to add a call to stage2. Create that stage2 here with make-c stage2 all, and then the clean call would just have to call clean on stage2. Great. I guess we also need to do one other thing here in the makefile. We still have this second.bin, which is our, I guess, our placeholder stage2. We need to replace that with the actual stage2.bin that we have. And actually, let's make it official by deleting it. There we go. So I guess that's it. So let's give it a try. So make-b all. Okay. So helpers.inc doesn't know about the print. Right. Okay. It was expected. Was to be expected because this one here needs to be included after the macros. Otherwise, it will not know about them. Okay, and I guess now we have... hold on, let me just check something. Did we build the binary correctly? Okay, great. We'll have the... Okay, I think we have a bug in makeboot. So I think... Yeah, I've actually... put this here as I've already noticed that we had a bug, but let's try to find what that bug is. So let's start by doing an obj dump of the first stage. So i8086 -b, and we have a flat binary file, and we want to adjust the VMA to be So the address we're loading at now is we're basically relocating ourselves to 600, and we want to deassemble it, and then it's build bootloader.bin. Okay, so here what we're trying to do is we are trying to write the address of the second stage to where the bootloader is expecting it. So we have, if I go back to the bootloader code, here we have this address to start, which is 4 bytes of FF, and we will try to basically replace these 4 bytes of FF with 4 bytes which point to the actual second stage sector, right? So let's try to see what we are doing. Right, I'm trying to find the 4 bytes of FF. Okay, that's not it. Okay, so these are the 4 bytes of FF, right? And I already think I see what the issue is. So here you can see that we are at D1. So this one is D1. So this one should be D2. So why are we copying it to D0? Hold on 1 minute. Why are we copying it to D0? That should be D2. Okay. Well, that's great. Okay, that's great. Okay, that's fine. And also, I think we have another issue. So let's try to rebuild it. Yeah, so it goes on and on and on and on, but it doesn't find the magic bytes for some reason. So let me just go back to this makefile here. So we are actually using stage 2, which is our binary. So let's take a look at what stage 2 has to offer. So let's just dump stage 2 and check the very first bytes. Huh. Okay. Well, that's bad. That's bad. So we have right. Okay, I see it. So okay. So the way we did things here is that we have this helpers file, right, which defines these 2 functions, and it gets included at the top of this assembly file, right? And what does is that the what the assembler will do basically is it will replace this include directive with the actual content of the file. So that means that we are actually defining the print functions before our before the start of our I guess before the magic bytes. Let's just say it that way, and that means that the magic bytes are no longer the first bytes that that are on this file, on the start assembly file. So what I can do is I might just get away with just moving this down here. I think that should be enough, but let's give it another try and see. Okay, cool. So now we actually found the magic bytes. And if we take a look at the stage 2, I believe the first 2 bytes will be F41C. Great. Very cool. Very cool. Okay, so let's, I guess let's run this and see what we have. So let's go ahead and here with the box debug. I want to debug this because I want to see that we're actually doing everything correctly. So let's hit it with a breakpoint. And remember that we are getting loaded at address 0x800, but our first executable instruction is actually at 0x802 because it's the first 2 bytes are the magic bytes, right? So let's continue, and we've hit our breakpoint. So let's compare this XOR AXAX, that looks good. So let's just go all the way through all this. So here we are just doing the init boot info stuff. And now we are here doing the XOR EBX, which means that we are doing fine. So I want to go all the way to, I guess, this the int 15, and then we will take a look at what we have in the registers. Great. So here in the EDX, sorry, we have this value here. That's fine. In CX we have 0x14, which is 20. Good. In AX we have EA20. That's great. And I guess we just jump over that, and then we see what we have after this. Right. So let me just put another breakpoint. Let's disassemble that code from 0802 to let's say 0850. I just need a few more instructions. Actually, I need more than that. Let's say F0. Right, so let's look for the int 15, and here what we want to do is we want to be at 085e. So let's put that breakpoint down, 085e, right? Continue. Right, so we've executed the int 15 now. So let's take a look at what the registers look like. Right, so we have EAX, that contains the correct value. We have BX that contains the 1, which means that we've read the first memory map, and if we want to read the next, we need to read it from offset 1, which is good. And then CX contains the correct value because we've read 20 bytes, which is 0x14. And the rest looks good. And of course here our DI register contains the value of the, I guess, the address of mmap that we've set. So now let's go through the code and see. So we are comparing EAX to that address, and we know that it's already fine. It won't jump, and then it will move the first, I guess, the value in DI. Actually, let's take a look at DI, right? So DI, I want to look at 20 bytes, and actually I want to just memory dump them, and the address is DI, right? Great. So here we have, so this one here is the start. Oops, sorry. So this one here is the start address. This one here is the length, and this one here is the type. No, just this one here is the type because it's a D word. Right, so we have an address that starts at 0000. This is a quad word, so we are taking 2 D words, and then it ends at 000. Well, it ends at the lower half is this 9F00, and you can see that, as I said, the addresses and sizes are actually page aligned, so they will all be multiples of 0x1000 hex, which is 4K basically. And here we have the value of the type, which is 1 in this case, and 1 means that memory is available, right? So let's go ahead and check this. So now we've moved that 1 into AL, and now we are comparing it with 01, and we'll check. So now we've basically did the comparison. We found out that it was true, and we've jumped to this 3 here. So now we are moving the mmap 3 into AL, which is 1. And then we are jumping +6, which is to this anonymous label we have. Right, so let's go ahead and do the, we're moving the byte into the address, which is DI, and let's just redump DI again. I'll just take 8 for now. Right, so that's, if you can see here, we've moved this one here to this one here. So instead of taking a full byte, now we're just taking, well, instead of taking 20 bytes, we're taking just 16. So we're doing some memory economy, right? Okay, let's go ahead. So we add DI 16 to the I, we compare that the I didn't cross the the page boundary that we've allocated for it. And then we jump if it's not below. Otherwise, we know that EBX, we do the check for EBX now. And EBX is not 0. So if it's not 0, we are going to jump back. You can see that we have a negative offset. We're jumping back to next map here. So now what we are going to do is we are just actually going to let it run for a while. Of course, we have the breakpoint. So let me just delete that breakpoint. It's breakpoint 2. You can see it here. So let me just delete that and give it the continue. So now it will run. And if I do a Control-C signal, you can see that it basically gives me control again. And we can see that the instruction that we are executing is this jump -2, which is basically this jump forever, right? So now what we are going to do is we are going to look at the address on which we've put our boot info, basically. So we know that it's 8 3 zeros. So let's take a look. Actually, I need a bit more than just 10. So just take 64, right? Right, looks good. We have some data there. So it's, I think we've skipped something. Hold on a minute. So that. Right, okay. So let's see. So this is these are the magic bytes, right? This is the size. So C0 is, hold on, let me just check with our calculator really quick. It's 192 bytes. We have 96 bytes of the boot info, but we know that it's, I guess, a static size. And then we have the difference being another 96 bytes, which is the size of our memory map, right? Okay, so let's take a look at that. So here we have, so let me just pull up the, where did I put that? Yeah, there you go. So the bootloader is 0, so it's this byte here, should be this byte here, or rather here. And then the frame buffer pointer is a quad, so it should be this, and this, or rather this one. Then width, height, and scanline and pixel format, that should take us all the way down to here with the paddings. And here you can see that we have the, and also the ACPI and the padding for that. But here we have our memory map. So starting at A060, right? So 0x60 is 96, which is basically the size of this. So here at 0x60 we are here, and you can see that we have this first map or memory region that starts at 0, has a type of 1, which is free, and has a size of 9F000. And then we have another one that starts at 0F000 and has a type of 0, of course, which means that it is reserved and has a size of 1 page, 1000. Same again, we have this memory here that starts at E8 000 and has a type of 0, which means that it's reserved. And it has a size of, well, basically 0x18000. And here we can go ahead and look at the other ones. So we have another memory here that's free, has this size. Another one that has the ACPI actually this time, has this size. And then here we have another one that's reserved with this size. And then we have, right, so this is the very last value that we've read. So it was A2, which means that it was reserved and it was translated to 0. So basically we are reading, every time we are reading this much, but we are moving this value here, and we are moving our cursor here. So we are rereading this much and overriding this, except for the last value because we're not overriding it, right? So this we don't really care about because our size points to this as the last value. All right, great. So now we have A memory map. All right, I guess that's it. So we have a working memory map that we can use to basically implement a memory map or physical memory allocator. So how cool is that? I guess we will stop here for today. Next time we will work on the video stuff to choose a video mode and set it up. But we will reuse pretty much the same way of doing things. That's how the BIOS works. It uses the same concepts, I guess. Well, until then, if you have questions, leave them in the comments below. And if you have, if you want me to do a video on other topics or get into the specifics or something, let me know. And I'll tune next time. See ya. Bye.